Okay, then let's start. Yeah.
Okay, great. Okay, I'm going to go ahead and start. My name is Kurt Takara, and I'm presenting this paper, Accelerating and Improving FPGA Design Reviews Using Analysis Tools, on behalf of my co-authors, Anna Tseng and Ayari. So let me go ahead and get started. More and more reliability, data integrity, and functional safety requirements have become um, more prevalent in FPGA designs. These designs are often targeting safety critical applications that may require DO-254 or ISO 26262 compliance. On these designs, program risk management requires design reviews in order to ensure a project meets not just its schedule and budget requirements, but also avoids functional issues in system deployment. There are many challenges to achieving design quality and reliability using design reviews. Previously, manual design reviews were a mainstay, but with today's designs, manual reviews are not sufficient and don't scale with increasing design sizes and complexities. Often, design teams are developing review checklists that focus on issues that they have encountered on previous projects, and instead of focusing on issues that they may encounter on their new design with new design styles or architectures. Manual reviews are also time consuming and error prone. And finally, design reviews are always under schedule and budget pressures. So all these challenges create a need for a more automated design review flow. In order to successfully automate design reviews, a flow should be built on design analysis tools. Leveraging design analysis tools will allow project teams to check their designs against the latest industry standards and best practices. Automation with design tools provide higher performance with more consistency and lower review errors. An automated flow enables a more well-defined and repeatable review process. So here's an example of an automated FPGA design review flow. This automated flow will help to improve design quality and improves design review efficiency and productivity. Using this flow, design teams will be able to complete design reviews not just faster, but also more consistently. Although this flow shows all these tools running in series, oftentimes these steps can be run concurrently, right? So you don't need to complete, for example, lint before you can start advanced lint. So these can be run concurrently. Once this review process is completed, the design can be given a clean bill of health and the design is ready for implementation, right? So as you can see, what I'll be covering is lint, advanced lint, unknown checking, CDC, and RDC. All these are, right now, these are all pieces of a design review that can be automated with design automation tools. So starting with lint, lint tools are static code analyzers that have been in use since the 1970s. So they've been in use for quite a while. Lint analysis is an automated way to check the RTL code. Since the RTL code is an abstraction of the FPGA hardware, it is important to check for problems that occur in the implementation of the FPGA gates from the RTL, right? So these are scenarios that sometimes simulation won't be able to find. So, so running simulation alone will not detect all these issues and that may result in a bad FPGA implementation. Lint analysis will ensure that your RTL conforms to industry best practices, as well as it will detect problem constructs such as ambiguous code, incomplete sensitivity lists, combinational loops, incomplete state machines, and underflow and overflow conditions. Lint can also enforce RTL compliance to industry standards or even project-specific standards. So some of these standards could include, like, for example, DO254, or even include company design guidelines. Finally, the early examination of the RTL at syntax, semantic, and structural levels will reduce design costs by detecting problems early in the project flow. So manual code reviews are both tedious and error prone. So here's an example where a designer can introduce unintended ambiguity, right? So if you look at the sign statement, by not including parens in this signal assignment, the intended order of operation between the two shift operators is ambiguous. So in this case, lint analysis will flag an error and require that the designer add parens to this assignment. Because manual reviews may not always catch every problem, lint analysis is a more efficient, thorough, and less error-prone way to detect design issues. So once lint analysis is complete, advanced lint can be applied to a design. Advanced lint uses stronger analysis engines beyond a structural lint analysis. So here, formal analysis technology is used to do deep sequential analysis to find issues such as deadlock of state machines, variable overflow, and combinational loops. But similar to lint, design teams can utilize this technology to find issues that would not be found in a manual review. And finding these issues in simulation or the lab may be more difficult and or time consuming. So here's an example of a deadlock condition. This state machine goes into deadlock when the signal has a value of 0. Advanced lint would not only be able to detect the state machine issues, but it can also provide a debug infrastructure to analyze and fix these issues. Yeah, so using advanced lint is less expensive and more efficient to detect these issues using formal analysis technology. And it'll find these issues earlier in the project flow and often before simulation is available, and oftentimes with a lot less effort than simulation. Often designers don't focus, Often designers don't focus on initialization and reset. Although sometimes oftentimes FPGA hardware initializes at power up, but more advanced designs often now contain, excuse me, many resets and independent reset functions and domains. If RTL logic is uninitialized or corrupted, design signals would be at an unknown value or X value. So if a critical signal or register becomes unknown, your design may malfunction. Additionally, there may be cases where design initialization or even low power mode entry or exit could corrupt design logic. Designers must also be aware that the differences in handling X semantics in synthesis and simulation can hide X issues and their effect on design logic. So designers should not rely on simulation alone to find these issues. Also, these reset and initialization issues will result in intermittent design errors in the lab. So designers may waste a lot of effort debugging these issues in the lab. Here's an example. Here's an illustration. Oh, sorry. Here's an illustration how X states are handled differently in simulation synthesis, right? In the case of X pessimism, simulation will pessimistically propagate an X value, where synthesis will have a good logic value. In the X pessimism case, when select goes to an X value, simulation would propagate an X at reg A, but in silicon, reg A is a known value as it is dependent on the signals I0 and I1. In the case of X optimism, simulation will optimistically propagate a deterministic value. But in silicon, the logic would be an unknown value. In this example, the else condition becomes active when select goes unknown, so the simulation would always propagate a 1. But in silicon, we don't know what reg A would be. So reg A would be unknown in silicon if select goes to a 1, or select goes unknown. So X states can be generated during circuit startup or initialization, during low power or multi-mode operations, or from simulation synthesis semantic inconsistency. And these can all lead to bad silicon. While finding issues with unknowns can be difficult with manual reviews, formal tools can verify that an RTL design is safe from X issues. Exhaustive formal algorithms are used to detect X corruption, although these issues may be missed by manual design reviews, or even maybe missed in simulation or lab testing. By using an automated analysis tool, designers can easily and exhaustively verify their design for all X states, X state issues, including initialization and post-reset X issues. For designs with multiple asynchronous clocks or reset domains, manual reviews of domain crossings are very tedious and error-prone. When designs have asynchronous clocks, these are situations where clocks may have non-deterministic phase relationships, so these clocks are considered asynchronous. Clock domain crossing paths occur when signals are transmitted from one asynchronous clock domain to another asynchronous clock domain. And today's designs can have tens of thousands of CDC paths, and sometimes we're seeing designs with greater than 1 million CDC paths. So as you can imagine, these designs are very difficult to review for CDC analysis with manual processes. So CDC paths can be problematic because the source register clock is asynchronous to the destination register clock. So in this case, if you see that signal will change in the setup and hold window of the receiving register. So in this case, the orange TX register will change asynchronously to the blue RX register, which will cause the blue RX register to go metastable. So the violation of the setup and hold window of the RX register will cause that register to go to metastable, and that means that the RX register will settle to a random value. So this non-deterministic value on the RX side can cause functional problems in a design. Designers must add synchronization logic to prevent metastability from propagating to downstream logic. So in general, we want to prevent the metastability at the blue register from propagating downstream. So by adding a synchronizer, we can do that and protect there's a design against metastability. As FPGA designs get more complex, the number of crossings exceed the limit of what can reliably be reviewed by manual design reviews. CDC analysis tools enable the automation of manual CDC reviews. for CDC analysis, constraints enter the flow for the first time. So constraints are required to specify asynchronous clock groups in the design, as well as the clock domains of the input and output ports. At this point, manual design reviews will encompass both the design and the design constraints. Unlike with previous analysis, corrective actions from manual reviews may be to modify the design constraints rather than the design RTL itself. Constraints review is another burden on the manual design review process, but this automated flow enables an automated and more thorough constraints review also, in addition to the CDC design review. This automated flow will not only identify errors, but will generate a comprehensive list of all CDC paths and their associated structures for tracking and review. Again, we know that sometimes FPGA hardware initializes at power up, but reset domain crossing paths or RDC paths occur more often in today's complex FPGA designs. Complex designs integrate multiple IPs, and each IP can often have an independent reset. Reset architectures have become more challenging with safety requirements that in some cases require local resets to initialize bad or faulty logic while the rest of the design remains functional. So less often for some of these designs does a global reset work, and oftentimes designers may need to implement a local reset to actually fix a local problem instead of resetting the whole design. And due to the complex reset architectures in these cases, RDC paths and analysis are similar, but even more complex than CDC analysis. Similar to CDC paths, RDC paths can be problematic because the source register reset is asynchronous to the destination register reset. So an asynchronous reset on the source register, in this case, the orange register, will generate an asynchronous signal that would change in the setup and hold window of the receiving register, in this case, the blue register. If the blue register's reset is not asserted, so if the blue register is functioning and this violation occurs, the blue reset will become metastable and settle to a random value. If this happens while the destination domain, so while this green domain is functional, this non-deterministic value can cause functional problems in the design. RDC analysis tools enable the automation of manual RDC reviews, similar to CDC reviews. Constraints are also required to specify asynchronous reset groups and the reset domains of the input and output ports. By incorporating RDC analysis, both the RDC analysis and constraints review process are automated. So similar to RDC analysis, similar to CDC analysis, the RDC analysis will also generate a comprehensive list of all RDC paths and their associated structures for tracking and review. So just because you're using an automated tool doesn't mean you lose the visibility into all the pieces of your design, including all the CDC and RDC paths, as well as the constraints information. So in order for an automated FPGA review flow to succeed, the tools and infrastructure must meet the following requirements. The tools must be available and accessible to all designers. Some recent logistic challenges include designers or engineers working from home. So in today's environment, more and more designers are working from home. So tools need to be able to, so the tools must be available on both Linux and Windows platforms potentially to allow all designers to access, whether at home or in the office. Also, tools must be available to designers throughout the design flow, but especially available early in the design flow when bug fixes have a lower cost. So the recommendation would be to start running these checks as soon as possible, because the sooner any issues are identified and fixed, the less work it is for the designer, and the lower the cost is for the project team. Tools must also be configurable to allow teams to specify their own review criteria and create project-specific rule sets and checks to meet quality and safety standards. In terms of being identifiable, tools should provide checks and violations that are easy to review and debug, as well as provide suggestions for design issue resolution. Repeatability-wise, repeatability is needed for design reviews to enable consistency of results with the same design, and demonstrable repeatability is also required for several safety standards. And finally, auditable results are also required for tracking purposes and for designs to meet safety standards. So tracking is not only important for design teams to be able to monitor their progress, but it's also necessary and required for some safety standards. An automated FPGA design review flow was presented just now, and this flow addresses the shortcomings of manual design reviews, including time-consuming and error-prone manual checking. By using design analysis tools, teams are able to easily check their designs against the latest industry standards and best practices. This flow delivers improved performance and productivity over manual design reviews. We described a well-defined review process that is consistent and repeatable. So in summary, FPGA design reviews are a critical part of the design process that is fundamental to mitigating risk. Although manual design reviews have worked well in the past, unfortunately, they do not scale to the increasing complexity and size of today's FPGAs. We have described an automated tool-based design review that allows for faster and easier design checking, as well as meets the audit and archive requirements for industry safety standards. Finally, the design review challenges and this automated flow are applicable to ASICs as well as FPGAs. So with that, I'm open to taking any questions.
Okay, thanks a lot. There are any questions? You can unmute your mic if you have a question. No, if there's no questions, okay, then we can finish this talk. Thanks a lot.